Let us see now what is meant by Zeroth Law of Thermodynamics. Statement. It states that two systems are in thermal equilibrium with third system separately then that two systems are also in thermal equilibrium. The statement of thermodynamics zeroth law, it goes out like this. It states that two systems are in thermal equilibrium with the third system separately, then that two systems are also in thermal equilibrium. So let me consider that the first two systems are A and B, system A and system B, and the third system is system C. So I'll try to explain this concept of zeroth law with the help of a diagram now. So see now. Let me consider this is my system A with some matter. This is my system B with some composition of matter, and now these two systems are now connected with adiabatic wall. In between the two systems there is an adiabatic wall. Adiabatic wall is nothing else but it's an insulating wall which will not allow the transferring of heat energy. So it is now connected with an adiabatic wall between the two systems. Now let me have another system C, which is again composed of some matter, and this system C is connected to two systems by conducting wall, which we can even call it as an diathermal wall. It's a diathermal wall. So see now, if I am having the two systems, system A, system B, which is composed with some matter, and now these two systems are not in thermal equilibrium. These are not in thermal equilibrium. Now if I try to put these two systems in thermal equilibrium with system C, what does the statement states? It states that the two systems are in thermal equilibrium with the third systems. It is in thermal equilibrium with the third system separately. It means that since here the system C is connected to system A through a conducting wall, then definitely what happens? There will be transferring of heat takes place between system A and system C. And in the similar case, system C is connected to system B through a conducting wall. So that's why the transferring of heat takes place between system C and system B. So now what happens here? Whenever the transferring takes place, the parameters of the thermodynamic systems will be changed or will be altered, and that alteration of the parameters takes place until the transferring of heat takes place. Once the parameters on both the systems are same, then the transferring of heat will stop. If the transferring of heat is stopped, or the flow of heat energy from one system to another system is stopped, we can say both the systems are in thermodynamical equilibrium. What does it mean? If the systems are in thermodynamic equilibrium, it means that it is having the same parameters or same thermodynamic variables. So now system B and system C are in thermodynamic equilibrium. It means that the parameters of system C is similar to the parameters of system B. So I can say the system C is in thermodynamic equilibrium with system B. Now here also, the two systems are in thermodynamic equilibrium with the third system. What are the two systems? System B, system A. Now these two systems are separately is in thermodynamic equilibrium with the third system separately. Means what? These two systems are separated by some insulating wall. It is an insulator, so you cannot expect any kind of heat transfer between A and B. There is a conducting wall between system B and C, and also between system C and A. So the heat transfer only takes place between C and B and also C and A. So because of this heat transfer, these two systems, system C and C and B, and system C and A will come into thermodynamic equilibrium. Whenever these two systems are in thermodynamic equilibrium, then automatically these two systems are also in thermodynamic equilibrium. Let me give one example how these two systems which are separated by an insulating wall or adiabatic wall are in thermodynamic equilibrium with respect to temperature. I will take an example of temperature. I will show that these three systems are in thermodynamic equilibrium with respect to temperature. So see now, once these two systems, system B and system C, comes into thermodynamic equilibrium, I know that the thermodynamic equilibrium is satisfied when the system is having the mechanical equilibrium, or the system is in thermal equilibrium, or the system is in chemical equilibrium. So I'll take an example of one that is thermal equilibrium. So now, if the two systems C and B are in thermodynamical equilibrium, it means that these two systems will be having the same temperature. It will be having the equal temperature. Let the temperature is equal to TB, temperature of B, system B is equal to temperature of system C. Temperature of system B is equal to temperature of system B. Now, where these two systems, system A and system C, are also in thermodynamic equilibrium. Now here, I will take this example with respect to thermal, that's with respect to temperature. Then here also, temperature of system C will be same as temperature of system A. Then what happens here? Temperature of system C is same as temperature of system A. So see now, if temperature of system B is equal to temperature of system C, then temperature of system C is equal to temperature of system A. We can say that automatically the temperature of system A is equal to temperature of system B. So I can say that the thermal equilibrium, the system B and system C are in thermal equilibrium, and also system A and system C are in thermal equilibrium. So then I can say that all these temperatures are same. Automatically I can say that the system A and system B will also be in thermal equilibrium. So anyway, one of the situation is satisfied. So automatically what happens? Completely all these three systems will be in thermal equilibrium, and then it will be in thermodynamical equilibrium once they are in even though if they are connected through this conducting or insulating, through this adiabatic wall. So now if any of the two systems are in thermal equilibrium separately, then this third system also will be in this one. Then these two systems also will be in thermal equilibrium. So this is a concept about what is meant by Zeroth Law of Thermodynamics. In the Zeroth Law of Thermodynamics, there will be three systems. Two systems will not be in thermal equilibrium, but the two systems will be in thermal equilibrium separately with the third system. So then if these two systems are not in thermal equilibrium, they will be separately in thermal equilibrium with the third system, so that automatically all the three will come into thermal equilibrium in this way, in this fashion. So that is the statement of your Zeroth Law of Thermodynamics. Now let me replace this wall. With an I'll replace the adiabatic wall with a conducting wall. Let me see what happens if I replace the adiabatic wall with a conducting wall. Now assume that this wall has changed to conducting wall. It has now made as a conducting wall. What happens here? If I change the wall, there will be no transferring of heat energy. The heat energy transferring will not take place, even though a conducting wall is placed between the two systems, where the adiabatic wall was there previous to that one. So now what happens? Why does the transfer of heat doesn't take place? Because already the systems are in equilibrium. Already the system is in equilibrium. There will be no difference in the thermodynamical parameters. So that's how the transferring of heat will not take place. So this is even applicable for the thermodynamic equilibrium also. Even in the thermodynamic equilibrium, if you change the adiabatic wall with the conducting wall, the transferring of heat will not take place. So this is a concept about what is meant by zeroth law of thermodynamics.